us about give an introduction to soft matter physics. So he gives 6 lectures.
Okay, it's a pleasure to be here. I thought I'd tell you just a little bit, just before I get started, about the history of soft materials as seen from the perspective of physicists. All right, so soft materials, people like chemical engineers have done soft materials for probably, I don't know, 70 years. But physicists took up the subject, or parts of the subject, starting as early as the 1960s. Liquid crystals, I'll tell you a little bit about them, became of interest to physicists in the 60s. The most notable name there is probably Pierre-Gilles de Gennes. And then also in the 60s, physicists began having some interest in polymers, and perhaps one of the first people there to make significant contributions was Sam Edwards from Cambridge University. In the 70s, things really started to pick up. Around 1980 or so, people started being interested in colloids. I'll tell you what all these things are. Don't worry if you don't know. And another center for colloids and liquid crystals and polymers was Paris, particularly outside of Paris at a lab in a town called Orsay. And since the 80s, it's become sort of a worldwide phenomenon with people not just in Europe, but in the United States and in Asia. And so that's a little bit of the history. So it's a relatively new field still to physicists. And it's a very interdisciplinary field. So you find practitioners of what we call soft matter physics who aren't physicists, who are chemical engineers, who are physical chemists. So it's a fairly interdisciplinary subject. So I want to start off by doing 2 things, or a few things. I want to answer some questions. What is soft matter? And I'll basically answer that by answering the question, what are some examples of soft matter or soft materials? And I'll try and cover all the different classes. And then finally, I'll try to answer the question, why are they soft? Okay, so actually the best way to answer question 1 is to answer question 2, rather than try and make great generalizations. So I'll start off with just listing some things that are soft materials. So polymers are soft materials. Polymers are, generally speaking, long chain molecules. So you have, polymers are made up of things called monomers, which are just a small molecule. And these, which I'll represent by, in a typical physicist fashion, it's a sphere, all right? So polymers are just chains of spheres hooked together. Long, linear chains of spheres that go on and on. Some examples are things like, I'll just give you a few. There's many, many. Polystyrene. So if you have plastic cups that you drink from, they're probably made out of polystyrene, all right? Another common one is polymethyl methacrylate. in popular language, these are usually called acrylics. So, for example, the plastic type of glass, you know, when you make an acrylic glass or acrylic transparent sheet that you use in place of glass, that's made out of primarily polymethyl methacrylate. So these are synthetic polymers. Let's see, some other, I'll come back. I'll give you more examples in just a second. But let me just stop there for now, and I'll come back to this and give you a few more in a minute. So the first example of a soft material is this class of materials called polymers. The next one is colloids. Colloids are basically small particles suspended in a liquid. All right, when I say small, I mean things that are anywhere from a few nanometers to a few microns. So they're very, very small particles suspended in a liquid. I'll give you some, some examples just quick are things like paints are colloids. You know, whether it's latex paint that you put on the wall or watercolor paints that you use, those are colloids. There's also some other types of colloids. I'll give you a little bit more detail on that in a second too. And then the next class is surfactants. All right. This is soap molecules, broadly speaking. All right. Now, soap sounds like it's not such a broad class of molecules, but a large part of you is made up of surfactants. As a matter of fact, in all of these cases, polymers, colloids, and surfactants, these are the sort of primary materials out of which biological matter is made. That is, excepting your bones, virtually everything else in you is either just a simple liquid, like water, or it's a polymer, a colloid, or a surfactant. I'll give you a little bit more detail in a second. But because of that, because these soft materials are the materials out of which biological matter is made, there's a close relationship between soft matter physics and biophysics. And so you'll find practitioners in the field of soft matter physics often do some biophysics, or they go back and forth between doing biophysics and soft matter because the two are very closely related. Then another one that I've already mentioned is liquid crystals. And then, let's see, did I want to list any others? All right, these are the main ones I want to concentrate on. There are some other things that people have added recently, things like granular matter, all right? And granular matter is a sort like sand when we talk about granular matter. There's also, I should say, a lot of work in the soft matter community on glasses, all right? Now, glasses aren't necessarily soft, but historically the way that's come about is because colloids can be glassy, all right? And I'll say a little bit more about that later in the week when I talk about colloids. But it's, this brings up an important or an interesting point about soft matter, and particularly about the sub-branch of soft matter that deals with colloids. And that is that colloids, being small particles suspended in a liquid, often behave a lot like regular liquids or regular solids. The difference being that the primary constituents, that is these small particles, can be large enough that you can see under a microscope. So colloids have often been used as model systems for understanding even molecular or atomic materials. And the reason is, the thing that's so nice about the colloids is they have many of the same properties under some circumstances as molecular and atomic solids, but they have the advantage of you can look at them, you can actually see them under a microscope, which you can't do so easily with atoms and molecules. In particular, you can follow them in real time. That is, you can watch their dynamics. The other thing is that they're also slow. That is, the dynamics are slow, so you can easily follow them under a microscope. So particularly in this sub-branch of soft matter, there's a close connection with the rest of condensed matter physics because of this analogy. Okay, so these are the primary ones I'm going to talk about. I'm actually not going to talk a lot about liquid crystals just because I only have 6 lectures and I can't do everything. And it's sort of a subject unto itself. But I'll say a little bit about it this morning. All right, so let's say a little bit more about polymers. So I've already mentioned that polymers can be plastics. All right, and I gave you some examples, polystyrene and polymethyl methacrylate. So these are synthetic materials. Another important class of polymers is rubber. All right, so rubbers are things like polyurethane or polyvinyl chloride, PVC. So I'll tell you a little bit more in just a second about why rubbers have the material behaviors they have. But let's just list the different things now. They're also used as adhesives. So for example, the adhesive, the thing that makes Scotch tape sticky, that makes it adhesive, is polymers, all right? So what's on the sticky side of them is various kinds of polymers. They also serve as lubricants. Think motor oil. They also appear, this is sort of a funny one, I'll call them viscosity modifiers. They're used a lot in various personal care products, sometimes simply to make the liquid in which they're dissolved more viscous. If you don't want it to have the viscosity of water so your liquid pours out real fast, but that it pours out more slowly, for example, things like shampoos or things, sometimes certain other cosmetics, they put polymers in simply for the purpose of making it more viscous. Let's see, what else? So these are all synthetic. All right, now I said that all of these play a big role in biology. So some non-synthetic polymers. First is proteins. Proteins are polymers. They're made up of, the monomers are amino acids. Maybe you know there's on the order of, there's a whole bunch of amino acids, hundreds, but there's about 20 amino acids that occur naturally and make up proteins. All right, so proteins are simply long linear chains made up of different sequences of these amino acids. They get their function, interestingly enough, not by existing in this long chain-like state, but by crumpling up and folding in on themselves. And what's amazing about proteins is they have this long chain-like structure, and yet they fold into, at least the useful ones, fold into very specific structures that do different functions. For example, there are proteins called motor proteins that appear in your muscles. And when you do something like this, like contract your bicep muscle here, there are little fibers in your muscle, actually parafibers, and attached to the pairs of fibers are little proteins called kinesin. And they actually have two legs that walk along the fiber, all right? And when you're contracting your muscle, that's what they're doing, all right? They're walking along the fiber. So that comes from a long chain polymer folding up into a compact state. And so the kinesin consists of a little bit that's a sort of a head and then two legs that walk like this that get activated chemically to do the walking. Proteins are basically just folded up polymers. Then the other important examples are DNA and RNA. These are made up of things called nucleotides. Those are the monomers, all right? And of course, DNA and RNA carry the genetic information that we all have, and that genetic information is basically used to tell various cellular machinery how to make different proteins. All right, so these contain the code for how to make different proteins. What does it mean to make a different protein? What it means there is the DNA contains the code that for a specific protein tells what sequence of amino acids it should make. So a typical protein might have, I don't know, 50 or 100 amino acids, and they're arranged in a specific order. And that specific order is coded by genes, which are just segments of DNA. So in a typical human DNA molecule, one molecule, it will have on the order of 10 to the 7th nucleotides, all right? And then little subsections in that linear chain. So it might be, actually the DNA stretched end to end can be on the order of about 1 meter, all right? But it's all folded up. But little segments of it correspond to what we call genes, and those genes are specific sequences of codes that tell how a particular protein is to be made. All right, so you see here nature uses polymers in a very sophisticated way to control the manufacture of proteins. The other, another polymer that appears naturally is a lot of different polysaccharides, sugars and so forth. That's some examples of polymers. Now, as for their architecture, I told you back here that they're long chain-like molecules. Like many things I say, my first pass is a little bit of a lie, and so now we'll try and straighten that out. If we want to think of it as a chain-like molecule, then you might draw out something like this, all right? And like I said, things like polystyrene and polymethyl methacrylate are usually like that. But sometimes you have different other architectures. So this is a linear chain polymer. You can also have branched polymers. And what that means is as you go along the backbone, there might be a branch coming off. And so this might go like this. There can be a branch like this, a branch like this, branch like this, branch like that. And then if that's not complicated enough, you can have branches on the branches. So, so this is a different architecture. And this appears in different kinds of plastics, like plastic films are sometimes branched polymers. One thing that's interesting about branched polymers versus linear polymers, if you make a material out of the same stuff, but one is branched and one is linear, the branched one usually will tend to be much more viscous. All right, it won't flow as easily. And that has to do with the way the different polymers are entangled with each other. So in a later lecture this week, I'll talk a little bit about what's called the rheology of polymers and of other soft materials. Rheology is the study of how a liquid flows. All right, so one thing that's characteristic of soft materials is their flow behavior is quite a bit different and in general much more, you can choose your word, complicated or rich. All right, I prefer rich, all right, because it's one of the things that's kept me busy for about 30 years and managed to keep a paycheck coming in is I get to study some of this flow behavior. Yeah.
In your branched polymers, can there be loops?
There can be loops. It's not so common. It's not so common, but there can be loops, and it's interesting because if you take a linear polymer and you simply put a loop in it like that, its rheological behavior will change dramatically. It will become much, much, much less viscous. All right? So it's and this is sort of a topic of some current interest. My colleague at NYU, Shura Grossberg, has made a number of interesting discoveries here and contributions to the theoretical literature. Other people have done experimental studies. But yes, there can be loops. And interestingly, if I take a linear polymer and I break the loop, those two, you'd be able to tell the difference between instantaneously. The looped one would flow very easily. The unlooped one would flow in a much more difficult way. All right. So people should feel free to interrupt me and ask questions. Let's see. I have these notes here because I want to remember all the things I'm supposed to tell you. Oh, all right. Then the next branched, I left out the end there. The next one is cross-linked. All right, so one thing that chemists who make polymers can do is they can take linear polymers like this, and say there are several of them, and they can link parts of them together like this. Where they cross, they can link them. You can have another polymer coming in here. Not all of these will necessarily be cross-linked. Maybe that one maybe they just pass like that over each other. But at least some of the places where they cross, they actually have, the way it's usually done is you put a different molecule here, all right, along the chain. And whereas normally a molecule in the chain can link to two neighbors like this, the different molecule you put here can link to 3 or more. So you can have cross-links like this. They don't have to be like this. You could have them come off like this, you know, so just a branch of 3 and then come over here like that. This is what makes rubbers rubbers, all right? That is the fact that they're cross-linked. So natural rubber, what people discovered is that by exposing it to sulfur, you can make the natural rubber cross-link with each other, all right? And so they called that, sort of before they knew exactly what was going on, they called it vulcanization. But basically what it just meant is it meant taking natural rubber and cross-linking it. And so what happens, the difference between something that's cross-linked and something that's linear, this in general, not always, but in general will be a liquid. It may be a very viscous liquid, but in general it will be a liquid. This will be solid, like a rubber, all right? So you know when you have something that's rubber, you can deform it and it's elastic. It comes back to its original position, all right? Now, there is an important distinction to be made here. There's the glass transition temperature, Tg. All right, so if Tg is less than, say, the ambient temperature, room temperature, all right, then what you get is a rubber. All right, basically a rubber is a cross-linked set of polymers, but there's this glass transition, and it's important that the glass transition be below room temperature. If Tg is greater than whatever temperature you're working at, then what you get is a glassy material. That is, it's hard, all right? And that has to do with the interactions between the different strands. Those interactions between the different strands is temperature dependent. At high temperature, that is at temperatures above the glass transition temperature, they tend to be loose and floppy, and that's what gives you an elastic material. When T is less than Tg, they tend to stick together, and you get a glassy material that's not very elastic at all. It's a little bit elastic, but it's closer to being like a normal solid. All right, let's see how I'm doing here. Oh, then the last type of polymers I'll mention, the last class, which I just don't have time to talk about because it's too big a topic, is conducting polymers. All right, so conducting polymers, yes?
What's an example for the last one?
I'm sorry?
What is an example for the last one?
Oh, like this? Any
And the glass transition temperature is
glass transition temperature? Actually, it's done all the time in different materials, all right? As you can take polystyrene and you can cross, so polystyrene has a glass transition temperature of about, let me think, an example of the last one.
What about cooling the rubber?
Well, polyurethane is an example. Natural rubber is an example, all right? So those are some examples of rubber materials. So like I like to work out. When I work out, I'm on a polyurethane foam mat. That's a cross-linked polymer, and it has that elastic behavior. A rubber band is an example of a cross-linked polymer. Here's an interesting thing that I just thought of. So you take a rubber band, all right, and you can stretch it. One thing interesting about rubbers is they stretch a lot more than normal sort of solid materials. You know, they can easily stretch by a factor of 2 or 3. Maybe I'll have a little bit more to say about this later in the week, but are you familiar with silly putty? All right. Silly putty is really cool stuff, all right? Anybody who's played with it knows that. The interesting thing about silly putty is it sort of looks like a rubber, all right? That is, if you roll it up in a ball and you bounce it, it'll bounce off the table, sort of like a rubber ball will. But in fact, silly putty is not cross-linked, all right? What it has is very long polymers that are highly entangled with each other. And if you take some silly putty, roll it up onto a ball and set it down on the table and just watch it, or maybe go away, have some tea, come back in a half hour, you'll notice that it will have spread out a little bit. It actually flows like a liquid, all right? What's going on is you have very, very long polymers like this, linear polymers, it will flow, but those polymers are tangled up with each other, and it takes time for them to move around because of these entanglements. And I'll tell you about that specifically in a later lecture. One of the big victories of physicists in this field is the description of the flow behavior, the rheology of highly entangled polymers. The big names in that were Pierre-Gilles Dejean, Masao Doi, and Sam Edwards. These guys did a brilliant job in figuring out and explaining from a molecular point of view why something like silly putty can bounce if you drop it, but will flow if you just let it sit on the table. All right, so that's sort of an example of the interesting behavior, rheological behavior you can get. Okay, all right, so that's polymers. Let me tell you a little bit about colloids. We'll spend a fair bit of time on polymers, in part because of all the things in soft matter. Polymers have probably been the most important technologically. That is, our understanding of them has contributed a lot to technology. Oh, and the thing I wrote down here, which I'm erasing now, is conducting polymers. This is a big subject in and of itself. And I won't talk about it at all, really, other than to say a couple things. It really started developing around 1980 or so. Or actually, no, that's not quite true. It started developing in the early 70s. There's a place where physicists made a big contribution and understanding conducting polymers. Some of the names there are Alan McDermott, who was at Penn, Alan Heeger, who was at UC Santa Barbara, Richard Friend, who's at Cambridge. These are some of the notable people in this field. Conducting polymers have really started to come into their own only in the last 10 to 15 years. The idea is, the thing that's nice about conducting polymers, the idea is you can make essentially electronics out of plastic. All right? So the idea is you can make flexible displays, and people are already doing that. And in your phones, in your phone displays, many of them have conducting polymers that are used as electrodes. They're used essentially as wires and electrodes. But you can also make transistors out of them and other things as well. And there's a great deal of research in this area, motivated largely by the desire to make flexible displays. All right, so that's something that I won't have time to talk about. All right, so the next thing I want to talk about are colloids. All right, colloids are small particles suspended in a liquid. I'll talk about them more in another lecture. The word I've left out here, which is important, is suspended. So basically what makes a colloid is two things. It has to be bigger than a molecule. All right, so you can decide what's bigger than a molecule. Typically people say it's a particle rather than a molecule when it has a size of about a nanometer or two. All right, that sort of sets the lower end. So it's a little bit arbitrary, but that's normally what people mean. The upper end is set by, does the particle stay suspended in a liquid? All right, now what suspends a particle in a liquid? The thing that suspends a particle in a liquid is thermal motion, Brownian motion. So the particle has to be small enough that it remains suspended in a suspension, and typically that occurs when the particle is less than about 2 microns in size. It depends on the liquid, it depends on the particle, but roughly I'd say that these go from 2 nanometers to 2,000 nanometers, all right, which is 2 microns. Once particles get much above 2 microns, they almost always settle to the bottom of the container, all right? So that's a suspension, but not a colloidal suspension. That's the important thing here. Real important thing for colloids then is Brownian motion. Let me ask, has anybody at this school lectured on Brownian motion? You have heard lectures on Brownian motions, yes? No? All right. I need to know because otherwise I'll devote a whole bunch of time to it and you'll be sitting there going, what's he talking about this for? We've already heard all about it. All right. But I'll tell you something about it that I bet, I could be wrong, whoever lectured about it didn't tell you. As a matter of fact, whoever it was, is he here? Is she here? All right. All right. Good. I'll say. Did you tell them about hydrodynamics and the velocity autocorrelation function of long-time tails? All right, so he lied to you. All right. Virtually all statistical mechanics books lie to you, all right? So I'll tell you a little bit about the lie and why people lie to you like this, and when it's important and when it's not important, all right? But that's probably all. Well, I'll say a few other things about Brownian motion, but I won't go into it in detail because you will have heard about it already. Okay. I have to do this. The reason I do this is maybe just a personal one, but about 25 years ago, I did a series of experiments that were nice experiments that measured this particular aspect of Brownian motion, and I think it's kind of cool. At any rate, so small particles, they come in different shapes, all right? Spheres, rods, disks, whatever you can imagine, all right? The classic ones you sort of think of as being spheres, but they also are rods. Examples. All right, I already mentioned one, paint. So the latex paint that you typically paint on a wall is made up of tiny particles of usually polystyrene and polymethyl methacrylate. There's some other stuff thrown in there too, because it turns out polystyrene and polymethyl methacrylate are slightly too hard. And so they're mixed with other things to make the particles a little bit softer. That's what those paints are. And when they dry out, what they make on your wall is a very nice thin coating of plastic, all right? The color is given by pigment that they have in them. Pigment for white paint is usually titanium dioxide, which is another colloid. They try and put as little of that as possible in the paint because it's expensive. And then they put some other dyes in there to give it the color you want. Another example from biology is viruses. Viruses are basically colloids, and they get suspended in your blood, all right? And again, they come in the usual shapes. You can get viruses that are spheres. You get viruses that are rods as well. They come in a variety. Of shapes. There's physicists have studied viruses in a number of ways. It's becoming a popular topic now in the physics community to study how viruses assemble themselves and what the rules are for that. Actually, the pioneers in that were Watson and Crick. It's one thing they figured out right after they figured out the structure of DNA. They did some beautiful work on this. But nowadays, a lot of physicists are getting involved in that. But viruses have also been used because there's they serve as model systems. So for example, there's a tobacco mosaic virus, which is a long rod-like virus. And there's other rod-like viruses that they're mostly a rod, but actually they twist around a little bit, and they're chiral. All right, and this chirality gives them very, very different properties, very special properties. So these have been studied by physicists for their physical properties and not just their biological function. Let's see, what else?
So these could have liquid crystalline orders.
Yeah, in fact, yeah, and yeah, that's absolutely right. So viruses can have liquid crystalline order, and the ones that are chiral do some particularly weird things because they're very long molecules, and that chirality, the effect of the chirality gets sort of amplified by their length. Let's see. Oh, clays. Clays are essentially colloidal suspensions. They're usually made up of disc-shaped particles, all right? And those discs tend to stick together, and that stickiness is what gives clays their characteristic mechanical properties. Structures. All right. You'll hear people talk about sols and gels. All right. A sol is just, see, how do I write it down here? See if I, yeah, just they're freely suspended particles. Gels, the particles are linked together. Let's see, how do I write it down here? Aggregated. So here, if you were looking inside of a beaker of water or some other liquid, your colloids would be suspended like this. They're sort of free. In a gel, the particles would be linked together and generally form some kind of random network, all right? So gels have very different behavior than sols. Sols, to a first approximation, behave mechanically like a liquid. You can pour them, whereas gels are very soft solids. All right, so that's something to keep in mind about them. One thing that's really fascinating is colloidal crystals. Maybe when I talk about colloids, I'll bring in a few pictures, just to flash on the board of colloidal crystals. These are gorgeous. What are colloidal crystals? Well, colloids, remember, I said, are 2 nanometers to about 200 nanometers. And they can actually form ordered arrays, all right, depending upon various properties. They need to have usually some repulsive interaction, and usually they need to be colloids where all the particles in the suspension are the same size to within a few percent. And then they need to be at a high enough concentration. If they're at a high enough concentration, they all have the same size, and they have a good, strong repulsive potential between them, they will form a colloidal crystal, which is just to say an ordered array of particles on a nice, perfect lattice in 3 dimensions. All right? Now, since the size, if you take particles that are, say, on the order of 200 or 300 nanometers in size, then the spacing between them might be on the order of, say, 250 nanometers. All right? What that means is you get Bragg scattering. That is, light will come in, and it's the same criterion you learned when you studied X-rays. If the difference in the path length is an integral number of wavelengths, then what you get is constructive interference. And so what you'll see here is Bragg scattering, but instead of it being at 1 angstrom and it being for X-rays, it will be at something like a half a micron, that is, say, green light, all right? So if you look at a colloidal crystal, what you'll see is you'll see these Bragg reflections, and they'll have colors to them. And the color doesn't come from any kind of dye or any kind of pigment. It's a structural color. That is, it's a color that results from the structure of the colloid. This has become a big area of research. I'd say this got going maybe in around 1980 for, I'd say, the first 15 years of people studying colloidal crystals in some, fairly extensively. It was just done for the fun of it. It was just a curiosity. People were interested in it. A guy named Pavel Puransky, who was at Orsay outside of Paris, sort of got people going in this, and then a lot of other people jumped in. Nowadays, it's become something of an important area of research for some of its practical applications. One is companies like Samsung are developing these colloidal crystals for display applications. So, for example, where this Bragg scattering occurs depends upon the spacing. One thing they do is they apply an electric field which changes the spacing, all right? And so you can change the Bragg reflection by the application of an electric field, and this can be the basis of a display technology. Another application that's really interesting that is being used, but not as much as it could be if we made some more advances in our research, is the idea of making a material that has a photonic band gap, all right? So if you remember, semiconductors have electronic band gaps, and the electronic band gap in general comes about because you have a periodic potential, and certain materials have a periodic potential that leads to a range of energies where electrons don't propagate through the material. We call this a band gap. Well, in principle, it's possible to do the same thing with colloids, with a periodic arrangement of dielectric particles. For certain structures, you can actually get a photonic band gap. That is a range of frequencies. And remember, energy corresponds to frequency just through E equals h bar omega. You can get a range of frequencies where light doesn't propagate through the sample. And there's hope that this could be used in all optical circuits to make things like waveguides, optical waveguides, optical switches, transistors essentially, and things like this. So this is a very active area of research these days. Let's see. Okay. One thing, all right, I'll say more about that in a second. All right, so that's a little bit of an introduction to colloids. The next thing I want to talk about is surfactants. Surfactants is sort of short, I believe, surface active agents, all right? So the old adage, oil and water don't mix, is what surfactants are all about, all right? They're about making a liar out of that statement that oil and water don't mix, or working with that. All right, so what are surfactants? Well, the first thing you have to understand is you can divide the world of liquids in terms of their solubility, roughly speaking, into two types. There's polar and nonpolar. polar liquid is something like water. It's the classic polar liquid. You have a big oxygen atom, and then you have two little hydrogen atoms. The oxygen likes electrons more than the protons do, and so that leaves a little net plus charge up here and a little net minus charge down here, and so it has a dipole moment. It's a polar liquid. All right. Benzene. Actually, it's probably not the best one. Benzene's not the least polar of all things, although I'll leave it up there. It's fine. It can be polarized a bit. But, and typically, what we find, and I'll talk a little bit more about this in the next lecture, but typically, polar liquids will dissolve in other polar liquids, and nonpolar liquids will dissolve in other nonpolar liquids, but they won't dissolve in each other. All right? So, and so what a surfactant is a surfactant is playing games with this. A surfactant is a molecule that has one part that's polar and another part that's nonpolar. All right? So the typical structure is you have a small polar head and you have a hydrocarbon tail. All right? So this tail, this is polar, this is nonpolar. This part likes to dissolve in water. This part doesn't like to dissolve in water. All right? So these molecules are extremely useful, and you wouldn't exist without them. All right, so some examples. Or what do they do? So if I take a surfactant like this and I stick it in water, what it will do is it will form little structures like this. It'll form little spheres made out of a bunch of these surfactant molecules, maybe on the order of 50 or 100, all right? Maybe even fewer. But the point is that the head groups, which are polar, will touch the water, and the tails, which don't like to dissolve in water, will hide from the water by all aggregating together, all right? So in that way, it can lower its free energy and dissolve in the water. These things are called micelles. All right. If you take a surfactant and you stick it in oil, it'll do just the opposite. It'll stick its tails outward and hide all the heads together, so that it can satisfy its solubility requirements. So these are both micelles. While it's purely arbitrary, people tend to think of these as normal micelles because they're in water and we deal with water a lot. And they often call these inverse micelles. All right? It's just jargon as far as that goes. Now, if you do this, suppose you have some water, and down here, actually, let's do it the other way around. I have some water, and then I throw in some oil, which tends to float on the water. All right? And then I throw in some surfactant. What will happen? Well, what happens there, if the oil is the minority component, is you'll get little oil droplets. I'll exaggerate it. And the tails will stick into the oil, and the heads will stick into the water. In other words, the surfactant goes to the interface, to the surface between the oil and the water. And these things will typically be very small. They might be 50 nanometers in size. And so this thing is called a microemulsion. And this is how detergents work. Detergents work, they get the oil, the dirt, out of your clothes by having surfactants in. And the surfactants go and they essentially help the oil to mix with the water on a length scale of maybe tens of nanometers. All right, so these are called microemulsions. Microemulsions are thermodynamically stable. There's also something called emulsions. All right, they're bigger oil droplets. Like this. So these are emulsions. These are maybe 50 nanometers or 10 nanometers. These are more like 1 to 10 microns in size. All right. These are either unstable, or if you're clever, you can make them metastable. All right. And when you wash your hands with soap, what you're doing is you're making emulsions. All right, and that's what's taking the oil away. This is the oil here. That's what's taking the dirt away. Is the action of these surfactant molecules. Now, all right, so I've told you about two structures, micelles and emulsions, either the micro or the regular sort. There's other structures that are even more important. One are lamellae. All right, one thing that, just when you think you know everything that a surfactant can do, it does something that you didn't think of. All right, so for example, you can make things like this. And so on. All right, so in this case, you'd have water here, and what you have here is a bilayer. That is, in this case, the surfactants have arranged themselves so their tails are back to back, and you just make a lamellar structure. There's all sorts of cool physics that goes on here. Back in the late 70s and early 80s, a German physicist named Helfrich developed a description of this and talked about all the different modes that can exist on this. So you can get waves that exist on this, and the waves can change the properties of the materials and how these bilayers interact with each other. But you are full of these things. Now, first of all, one thing that controls whether a material makes a bilayer or whether it makes a microemulsion or whether it makes a micelle, one of the things, is how big the head group is compared to the tail. All right? In other words, just geometrical factors. So there's a special, there are also surfactants that have two tails. And ones with two tails are more likely to make lamellar structures than ones with one tail, just because you need more space to fit them in here. All right? So every cell in your body is made up of a bilayer like this, all right? And they're made up of molecules called lipids, all right? And there's several different varieties of it. But lipids generally have a polar head group and two tails like this. In this, and it's it's the barrier between the inside of your cell and the outside of your cell. So if you take a bilayer like this and make an enclosed structure, all right? So what I'm imagining now is that this structure here is a bilayer. This is called a vesicle. All right, and so every cell in your body is a vesicle. Now, the bilayers in your body are a little bit more complicated in that they're not just this, but they have things embedded in them. They have things like proteins embedded in them. They make little openings that open up and let things in and close and don't let other things in. So your cell membranes are very fancy vesicles, very complicated vesicles. But nevertheless, this is another important class of materials. All right, so is there anything else? All right, so that's all I want to say about them. I want to see how we're doing on time. We're doing okay.
Indicate why microemulsions become unstable when they become emulsions, I mean, the droplet size.
No, well, all right, so one thing I haven't said is all of this depends, it depends not just on the structure of the micelle, it depends on the concentration of micelles, it depends upon the temperature. So you can get, for the same molecule, you can get phase transitions, where by changing the temperature, you go from a micelle to lamellar structure, and so you can get phase transitions between these different phases. All right. Oh, there is one I forgot to mention, and that is a cylinder. All right. So you can just have them arranged into a cylinder where they stick in like this. At the end of the cylinder, you usually have a spherical end cap. What's interesting about these can be short, all right, so the aspect ratio can be as short as 2, or they can be extremely long. That is, there are cases of micelles, of cylindrical micelles, that are that will span a sample that's a centimeter in size, all right. And the interesting thing about those is you get a long, so this dimension might be something like 20 nanometers, and this dimension might be a micron or 1,000 microns or a centimeter, all right? So at that stage, this cylindrical micelle looks a lot like a polymer. And in fact, the rheology, the way it flows, behaves a lot like a polymer. And in fact, with shampoos, for example, sometimes instead of putting a polymer in to give you a viscosity enhancement, they'll put in surfactants that form worm-like structures, and they act like polymers, and they give it that character. So that's another one. There's other things. There are so many structures that micelles make. It can be a lot of fun studying them. I will mention one final one, and this one's called a plumber's nightmare. And I have a hard time drawing it, but it's actually a cubic phase. What it is imagine you make a cube. This is the only way I know how to draw it, and you'll have to use your imagination somewhat. So suppose I have a cylinder coming out here, a cylinder coming out here, cylinder coming out of each face. And then these are connected inside, like this. All right, so they're just all connected. So what it is like 6 pipes coming together, all right, with a smooth connection between each of them. And that's a phase that is seen fairly frequently in micellar solutions. It actually makes a cubic lattice, all right, and you get Bragg scattering off of the cubic lattice. And somebody called it a plumber's nightmare. It becomes a particular nightmare if it becomes disordered. Sometimes these things don't connect up in nice cubic structures, and you get a disordered structure. So this is an extremely rich field with lots and lots of things that people have done over the years. All right. So then the last one I want to mention is liquid crystals. All right, so liquid crystals are basically anisotropic. They're made out of anisotropic molecules that display some kind of order, but not complete order. So what do I mean by that? Well, if I have a crystal like a colloidal crystal or a metallic crystal, all the particles are arranged in a nice crystalline lattice, and they have perfect translational order, all right? A liquid crystal, well, on the other hand, a liquid doesn't have any kind of translational order, all right? It's a disordered material. Liquid crystals, as the name implies, are something that's in between the two. So there's different kinds of liquid crystals, and perhaps that's the best way to illustrate what I mean. So perhaps the most common is called a pneumatic. These are typically made from rod-shaped molecules, not necessarily very big. So if we just draw a rod like this, in a pneumatic crystal, what you'll see is orientational order. But no translational order. So for example, it might look like this. If you look at the molecules, it's a liquid, so they're densely packed. They don't all point in exactly the same direction, but pretty close to it. So that if you look at the average direction in which they point, it actually defines a well-defined direction. And we say that such a liquid crystal has orientational order, and it's called a pneumatic. All right, so pneumatic just means one of this type. As you might expect, because of the anisotropy in the structure, these have interesting optical properties. All right, so in particular, they polarize light, and this is why liquid crystals are used in are useful for display technologies, because which way they orient can be manipulated from the outside, all right, rather easily. Another type is smectic. All right, a smectic liquid crystal might look like this. So what it has is orientational order. And some translational order. In this case, it has orientational order in that direction. It also, if that's the z direction, it has translational order in the z direction, but it's disordered in the x and y directions, all right? So in the xy plane, it's completely disordered. So it's like a liquid, all right? But in the z direction, it has translational order. There are also some wonderful variants on this. There are things called cholesterics, liquid crystals. And they are sort of like pneumatic liquid crystals, but so you'd imagine that in one plane, I don't even know how to draw it. So say this is a disk. Say I make a cut through it, and in this plane, all the molecules are oriented like this. In the next plane over, they might be oriented like this. And as you progress in this direction, the orientational order twists. And it actually has a chiral structure to it. Often this has to do with some sort of bend or in the shape of the molecule. So you get a twisting to them. All right, so cholesteric liquid crystals are also very useful in displays. You can get liquid crystals from disc-like molecules. So they stack up like plates. All right, and so those give you columnar or discotic liquid crystals. So there's lots of different ways that liquid crystals can order. But the thing that's fundamental about them is that they have orientational order for sure, and then incomplete translational order. Incomplete or no translational order. No translational order in the case of pneumatics, partial translational order, say, in the case of smectics. All right, so this gives you a little bit of feel for them. Now, the last thing I want to talk about in the last, I don't know, 20 minutes or so that we have, I want to try and answer the questions that I posed at the beginning. The first one being is, why are they soft? All right. What makes, one thing that distinguishes, or maybe the thing that distinguishes soft materials from other materials is that they're soft. Why are they soft? All right, now, the way you characterize the mechanical behavior, say, of a solid is you can do it by looking at the bulk modulus, which is just defined by this. If I have some material and I apply, say, an isotropic pressure to it, then I change the pressure, how much does the volume change? All right, so if I increase the pressure on this particle, you'd expect it to get a little bit smaller. Its volume will change, and how much its volume change depends on how hard it is. The harder it is, the less it changes. All right, so we characterize this by the bulk modulus, which is a proportionality constant K, and it's the change in V over V. And then there's a negative sign here so that K is positive. That is, if we increase the pressure, that will decrease the volume. And so we put a negative sign here so that the bulk modulus is positive. Another way to think about the elastic properties, so this is the squeezing hardness of a material. Another thing you can ask about any elastic material is how it responds to shear. All right, so if we take a material like this, say our cube again, what we do this time is we apply a force, a shearing force like this. All right, if this face has an area A, then we define a stress that's the force per unit area. This is the shear stress. Pressure is a form of stress, but different, applied in a different direction. All right, so this is a shear stress, and normally what you say here is that the shear stress is proportional to the strain. Now, the strain we usually denote by the symbol gamma, and it's, if I apply a stress like this, I go from having a material like this to having a material that's like this. This distance here we'll call delta x. This distance here we'll call delta y. Strain is delta y over delta x. All right. How far do you push it in this direction for each unit in this direction? That's the strain. And so we can define an elasticity. We usually denote it as G, which is proportional to gamma. So this is the shear stress. Now, if you look at both of these, you'll see that they have the same units. That is, stress and pressure have units of force per unit area. This variable, delta V over V, is unitless. Gamma is unitless. So K and G both have units of pressure. Pardon?
Is it delta y by delta
It's delta x over delta y, sorry. Yeah, thank you. Screwed it up. Yeah, good. Sorry about that. Okay, now, there's a simple way to look at this and to estimate what K or G is. Let's start with G. G is a force per unit area. But another way of looking at it is if I multiply this times a length, force times length is work. This is an energy per unit volume. All right, so what you're doing when you're pulling like this, you're giving a certain energy per unit volume. All right, and you might ask, well, what's the scale of that? How do I think about that? What's the scale of the energies and the volumes involved here? Well, typically for a conventional solid, the energy is going to be something like the binding energy. What's the energy with which two molecules or two atoms interact with each other that bind them together? So for molecular solids, this will be on the order of electron volt. All right? And this volume, well, this is the distance between atoms. So let's take something like copper. That might be something like 1.5 angstroms or 0.15 nanometers. All right. So if we do this, this is 1 times 10 to the minus 16 joules, 1.6 times 10 to the minus 19. I'm getting tired. And then this is 0.15 times 10 to the minus 9 cubed. And when you work that out quickly, you get a number of something like 5 times 10 to the 10 pascals, or 50 gigapascals. All right? And if you look up the shear moduli for things like copper and iron and things like this, what you'll find is that they're all on this order. Tens, maybe as much as 100 gigapascals, all right? And it's just energy per unit volume. The bulk modulus, K, there's a sort of general argument that it should be roughly 3 times G, all right? We'll actually, if I have time, we'll do that argument for polymers at least. And indeed, the bulk modulus is typically on the order of 150 gigapascals. All right, now, what about for soft materials? Well, the easiest one to deal with is colloids. It's just easiest to calculate. So for colloids, you have G is again E per unit volume. The typical interaction between two colloids that are, say, in a colloidal crystal, all right, is on the order of the thermal energy, KT. That's something to know about soft materials. KT is almost always implicated in the characteristic energies of interaction or deformation or almost anything. All right, you will see this come up again and again. It is an indication that entropy plays a really central role in understanding soft materials. So once you're into soft materials, you can hardly have a scientific discussion without entropy coming up. It's all over the place. Now the typical volume, remember I said these are like 1 micron cubed, all right? So you can work this out, and if you work it out, you get something like, well, here, let me do one intermediate step. You get, this turns out to be something like 4 times 10 to the minus 21 joules. And this is something like 10 to the minus 18th square meters. This is about, all right, this is the reason, the primary reason why this G is going to be so much smaller than that one. This one comes out to be something like 4 millipascals. All right. So, so they differ by about 13 orders of magnitude. All right. So soft materials are typically somewhere between 11 and 14 orders of magnitude softer than your normal materials. Now, most of that difference comes from this length change. All right. You have a factor of 10 to the fourth almost difference in the length. You cube that, and that's where you get about 12 orders of magnitude difference in the softness. Simply the fact that you have a longer length scale. All right. The other 2 or 3 orders of magnitude come from the interaction energy. The interaction energies are typically KT, which is, you can see, a couple of orders magnitude smaller than the typical interaction energies in a normal solid. All right, so this is an extremely important thing to keep in mind. It is the reason why, the main reason why soft materials are soft. Larger length scale, that's a principal reason. Weaker interactions, that's a secondary reason. All right, so then there's just a couple more things I want to say. All right, so one thing that's interesting is I told you you can have these colloidal crystals. So I didn't bring any with me, but if you ever get a chance, if you ever come by my lab in New York, I'll be glad to show you one. All right. And what will you see when you look at this colloidal crystal? First of all, I've picked a nice one, so it'll have nice Bragg peaks. All right, so you'll see colors. All right. The colors tell you that it's a solid. All right. It'll be sitting in a little glass bottle. All right. Then what you'll do is you'll tilt it, and it will flow. Why will it flow? Because the stresses involved just from gravity are big enough to melt the crystal. All right. In other words, you can melt a crystal with shear. Now, you can melt copper with shear. The problem is you have to shear it with about 10 to the 14th or 10 to the 13th times more stress than it takes to tilt than you get from gravity. And those kinds of stresses aren't typically available on the surface of the Earth. They are available deep in the core of the Earth, all right? But under normal temperatures and pressures, you don't melt solids by shearing them. But in principle, it's possible, all right? Here in these cases, they are so soft, you can melt them by shearing. And this brings into play here another important characteristic of soft materials. Their response is response to stress, let's say, is large and typically nonlinear. All right? It's like all things. If the stress is small enough, there's a linear regime, but the nonlinear regime is not irrelevant like it is in many materials. For soft materials, the nonlinear regime is always relevant. All right? So this is something that characterizes soft materials, is a large response to stress and in general, a nonlinear response to stress. All right, and it just has to do with this argument I just gave you about why they're soft. All right, the last thing that I want to say about them. All right, yes.
Another factor might be the dependence on history, shear history.
Pardon?
Shear history dependence.
Is shear? I still didn't understand.
No, I'm saying the response to stress.
Yes.
Could also depend on the history, the stress history.
Absolutely, absolutely. That's an excellent point. the response to how a material responds to shear depends upon its history. A simple example, although there are perhaps more relevant ones, if I shear melt this colloid, I go real fast and I melt it, all right? If I go right back, it'll go back rather easily because I've melted it. If I go out here and I wait a minute and I wait for it to recrystallize and then go back, I'll get a different response. So the reason I mention this is by shearing it, I changed the structure, all right? And so how it behaves to subsequent application of stress depends on how long I wait, and because that structure will recover or change in time. So it's true that the rheological response of materials is often, or is typically, time dependent. All right, and yeah?
You say that it's non-linear, the response is non-linear.
Yes.
Can it be non-monotonic?
What? Can it be what?
Non-monotonicity
I still didn't,
non-monotonic.
non-monotonic. Yes, it can be non-monotonic. There's some really cute examples of it being non-monotonic.
Cornstarch, which, so if you apply a shear rate, initially it shows thinning and then it shows thickening again. So we actually have samples downstairs, so
Oh, do you?
we can get them.
Maybe we can do some demonstrations of some of these things. This actually brings me to the last point I want to make, and that has to do with the dynamics. The dynamics are slow. Compared to normal materials. So one way of thinking about this is thinking about it in terms of the diffusion coefficient. So diffusion in liquids and diffusion of colloids is governed by an equation that says the diffusion coefficient is, roughly speaking, the thermal energy divided by the viscosity of the liquid times the size of the particle that's diffusing. All right, so right away, the fact that the structures in soft materials are much larger than the structures in hard materials or normal materials means that because this appears in the denominator here, the diffusion is going to be much slower, all right? Slower by at least say 4 orders of magnitude, comparing the size of an atom to the size of, say, a typical colloid, or even the size of a typical polymer. All right, so that tends to slow things down. In addition, these materials often have a large viscosity. All right. Polymers, for example, I already indicated a little bit. If you have long polymers, they get entangled with each other. And when they get entangled with each other, they become very, very viscous. All right? So this large viscosity and the large size of the individual constituents tends to slow down the dynamics. Now, for most of us working in the field, this, as experimentalists at least, this is a really nice thing, all right? Because it means that we can often study the materials just by looking in a microscope. We can actually see the dynamics. We can see these materials assembling, changing their state, because these occur on time scales of anywhere from, on the fast side, maybe 1/10 of a microsecond. Not much happens faster than that, or as slow as 100 seconds, or even hours. All right, and that entire time range in between, the entire span, is regularly observed in phenomena that we work with in the lab in soft materials. So these slow dynamics coming from the large length scales of the constituents and the large viscosities are characteristic of these materials. Okay, so that ends it for today. I think tomorrow I'll talk a little bit about solution behavior and phase behavior as particularly applied to polymers, with a few comments about how it goes to colloids. Then I hope to talk about, see, I can't remember the order. I'm going to talk about the rheological behavior, again, mostly of polymers, and then some about colloids, and a few other things as we go. So that's what we're up for. Okay, that's it for today.
So they will be there in the UPL?
Yeah.
We'll be there in UPL, so if you have any questions.
So it's at what, 4:30, yeah. Summarize a couple things. So we're going to talk about colloids today, and there's a lot to say. This morning, I'll sort of give you a background in the various kinds of colloidal interactions. We'll see how far we get. All right, but before we do that, I just wanted to summarize some things. Some of it we already talked about yesterday. So colloids are particles suspended in a liquid. They come in sizes from roughly 2 nanometers to 2 microns. We typically measure their concentration in the volume fraction of particles. So that can be as high as you want if your particles have different sizes. But if they all have the same size, the maximum density you can get is 74% by volume, which is the volume fraction of a close packed structure like an FCC or an HCP lattice. One thing to keep in mind about colloids is that they come in quite a broad spectrum of materials. We can make them out of plastics, out of inorganic materials like silicon dioxide or titanium dioxide. We can make them out of metals like gold and silver. Matter of fact, gold colloids have been used for centuries. They're used in stained glass windows, for example. They were used famously by Michael Faraday back in the 19th century. Some of his gold colloidal suspensions that he made back in the 1830s, 1840s are still on display at the Royal Society in London. You can actually see them. They're just fine. They're nice and stable. Then, as we said yesterday, they can be made out of other things like proteins or viruses. Milk is a colloidal suspension of fats and proteins. So they're little particles, about half-micron particles suspended in water. So they're all over the place. The other thing I mentioned is there are emulsions, and you can consider emulsions as a type of colloid. There, the particle, instead of being solid, is a liquid droplet, but you can have the same range of sizes, and to some extent you can think of emulsions as a kind of colloid. And most of the things that we have to say about colloids made from solid particles suspended in a liquid also apply to emulsions. And then we also talked about sols and gels. Now, I wanted to show you this so that you got a sense of what they actually look like, since I could only talk about that a little bit yesterday. These in the literature are some of the most famous pictures of colloidal crystals. They're from a paper right here by Peter Pusey and Bill Van Meegen, published in Nature in 1986. All right, so if you can see these, you can see that there's various colors. These, the volume fractions are given up here. The highest volume fraction is 52.5%. The lowest one is 39.4%. And what they're showing is a phase transition. Down here at 39.4%, what you see is a homogeneous disordered suspension of colloidal particles. Essentially at 39.4% and below, the colloidal particles don't touch each other and they just move around by Brownian motion and they take up random positions. All right, so as such, you can think of them as a liquid. The colloids themselves form a colloidal liquid, and so